properties at the end of alkyl halides, and to compare conditions under which SN1, SN2, E1, and E2 reactions occur. So let me begin with an example. And the example I'll start with is Tert-butyl bromide. We've, of course, been talking about this as an archetype of alkyl halide, tertiary alkyl halides. I could have just as well written tert-butyl fluoride here, or I could have well written any other tertiary alkyl halide. If we heat tertiary alkyl, tert-butyl bromide in ethanol, all right, ethanol, at, let's say, 55 degrees Celsius, so at a temperature above room temperature, then we get what's called solvolysis. Solvolysis means cleavage by solvent, solvolysis. And we see two products form under these conditions. One of them we've seen before when we introduced SN1 reactions. That's tert-butyl ethyl ether. This forms as the main product, forms in 72% yield. The other product, which I'll introduce for the first time from this reaction, a minor product, is isobutylene. And that forms in 28% yield. Now, one of the things I've pointed out in the past is that organic chemists often don't write balanced equations. So if I want to complete our equation here, I would also point out that at least as we're writing it, we're going to, in the formation of these molecules, we're also going to form HBr. I'll put that in parentheses because, as I said, often we focus on the organic products of reaction. And if I really want to be accurate about it, I should point out that in ethanol, you don't have molecular HBr, just like in water, you don't have molecular HBr. Remember, ethanol and water are very similar in their Lewis basicity. So in ethanol, HBr really is going to be giving us protonated ethanol, ETOH2 plus, Br minus. So the first of these products is the tert-butyl ethyl ether product is formed by an SN1 reaction, and the isobutylene product is formed by an E1 reaction. Now that's a big mouthful on this blackboard, and I'd like to take a moment just to review mechanisms for the formation of the first product, even though we've seen it before, and then we'll go on to the second product. So the formation of both the first product and the second product start with the ionization of tert-butyl bromide to give a tertiary butyl cation. In other words, bromine is a good leaving group, and we have a couple of conditions favoring ionization. We have a polar solvent, so formation of ions in ethanol or in water is favored, and a solvent like methylene chloride, which is not very polar, or hexane, which is completely non-polar, formation of ions is disfavored. We also have heat here, so we're heating this up. Under heating conditions, reactions go faster, but particularly reactions that give rise to two particles from one, entropy favors that. So under these conditions, bromine can leave to form a tertiary carbocation and bromide anion. Tertiary carbocation, as I pointed out, is not a species that you can put in a bottle. With very few exceptions, carbocations are very unstable reactive intermediates. The carbon, the center position only has 6 electrons around it. It desperately wants to get 8 electrons around it, so it has a complete octet. So one way this occurs, we've seen in the past. Here's our carbocation. Here's our ethanol. Ethanol has electrons. It's a nucleophile. The carbocation wants electrons. We draw our arrow, our curved arrow, flowing from the electrons to the atom that wants electrons, representing the formation of the bond. And finally, in protic solvents, protons go on, protons go off every Lewis base atom. So we've got tons of ethanol present. We've taken a sprinkling, a milliliter or so of our Tert-Butyl bromide and thrown in a big beaker of ethanol. So there's lots of ethanol present. So mass action just drives the deprotonation. In other words, we have a lot more ethanol than our other chemicals. And so ethanol pulls off this proton. And I'll show a curved arrow flowing from the electrons to the hydrogen. Of course, we can't have 4 electrons around the hydrogen, so we push electrons onto the oxygen. So this gives rise to our SN1 product. Now, there's a second pathway that the molecule can undergo, that the carbocation can undergo, and as I've already hinted, that's E1 elimination. That means elimination unimolecular. Carbocation can react with a nucleophile, having it attack in the pathway we've seen that leads to the SN1 product, but it can also react by losing a proton. So I'm going to write out the formation of the carbocation again, just so I give you a complete mechanism for the E1 reaction, but realize the carbocation is just undergoing a bifurcated pathway where we have 2 different processes under which it can react. This step, the first step, the formation of a high-energy intermediate, is the rate-determining step. That's why this is a unimolecular reaction. The rate-limiting step is the formation of the carbocation. After it forms, it's going to either react with a nucleophile or undergo the pathway I'm about to show you, which involves loss of a proton. So I'll point out rate-determining step. That means this is the slow step, and the other steps are fast. Okay. So what happens to our carbocation if it doesn't react with ethanol attacking it as a nucleophile? It can react with ethanol pulling off one of the beta protons. So I'll draw out the 3 hydrogens on the beta position. And here's our ethanol molecule. And so ethanol can act like a base to pull off this proton, push electrons in. And you notice what's accomplished in this flow of electrons is the same as what's accomplished in the other flow of electrons. In both cases, we're starting with a species, the carbocation, that doesn't have a complete octet. And by either borrowing electrons from ethanol, sharing electrons with ethanol, or by losing a proton, we're now giving 2 electrons to that tertiary carbon, and the result in this case is that we form the alkene. In some textbooks, you'll see the bromide taking off the proton rather than the ethanol. Honestly, in terms of what you write, it doesn't matter that much. I've chosen to write it this way. This is a little bit more correct because ethanol is more basic than bromide, right? You think bromide, it has a negative charge on it. It should be the thing to pull off a proton. That's reasonable to write that. But if you look at pKa's, HBr has a pKa of about -9, whereas we say H3O plus and hence ethanol, H3O plus is -1.7. Ethanol is going to be about the same for protonated ethanol, about -2. So ethanol is actually a stronger Lewis base. But that's okay. If you end up writing this as Br minus taking off a proton, same idea. Something is coming in and pulling off a proton. I'll just put this in parentheses. Anyway, regardless of how you write this, the rate of reaction, the rate of product formation is dictated by that first step. So in other words, rate depends only on the concentration of tert-butyl bromide. Once that carbocation is formed, the reaction is basically over and you go to the products. You go to this partitioning between a pathway that gives you the tert-butyl ether, the tert-butyl ethyl ether, and the pathway that gives you the isobutane. Thoughts or questions? Let's take a look at an energy diagram for the reaction on the right-hand blackboard. Yeah. Ah, great question. And this is one of the reasons why I'm so eager. This is one of the reasons why I'm so eager to summarize it. Great. Well, you've now just learned it's both. Both products form. So if you really are on top of this, you'll say, wait a second, it's not one or the other alone. We get a mixture, which is cool. I mean, this is the way nature works. Things aren't always simple. So in this case, in the solubolysis, meaning the cleavage in solvent of a tertiary halide, whether it's tert-butyl chloride, tert-butyl bromide, or some other tertiary alkyl halide, if there's an E1 elimination pathway that can occur, we'll see some E1 product. And if there's an SN1 pathway that can occur, we'll see some SN1 product. There are cases where you can't have any E1 product. So for example, we started with one of our first examples. I'm just going to write out pH because we're limited on space here. But when I introduced in chapter 6, when I introduced SN1 reaction, we didn't even have a name for it. I showed this reacting with various nucleophiles where we were getting the bromide replaced, including, I think, ethanol. Why can't we have any SN1, any E1 occurring with this bromide, with triphenylmethylbromide? No beta hydrogens. Each phenyl group is just a benzene ring attached. So there's no, I'll skip drawing a circle in the center here. So no beta hydrogen. All right, let's take a look at the energetics of this reaction. diagram for the E1 pathway. Not surprisingly, the energetics of the E1 pathway look very much like the energetics of an SN1 reaction. So I'll make a little chart with a reaction coordinate on the x-axis and energy on the y-axis. At some relative energy, we have our Tert-butyl bromide and our ethanol. The overall reaction is downhill in energy, the formation of our isobutylene, our E1 product, and our protonated ethanol, ETOH2+, and our bromide is going to be downhill. The reaction involves the formation of a high-energy intermediate, the carbocation. Here's our Tert-butyl carbocation, and I'll just also write the other reactants that are still present, ethanol and bromide. We go over an energy hump. The fact that the first step is the rate determining step says that the next energy hump is lower. We have a lower activation barrier, a lower energy pathway, a lower energy barrier that needs to be crossed to the product. And here's our product. And if I wanted to show both reactions, I'd simply represent a separate pathway with a slightly lower barrier for formation of the ether, of the ethyl Tert-butyl ether. So just to summarize, I'm going to say this is a similar profile to an SN1 reaction. And I'll say both our E1 and our SN1 go through a common carbocation intermediate. By common, of course, I mean shared carbocation intermediate. And that intermediate forms in the rate determining step. Thoughts? Questions at this point? What makes this reaction possible and what makes all of the SN2, SN1, E2, and E1 reactions that we've seen possible is that we have a good leaving group. The bromide in this case is happy to leave and take a pair of electrons with it. Why? It's a very, very weak base. Remember I said HBr has a conjugate acid, or bromide has a conjugate acid, HBr, that has a pKa of -9. HBr is a very strong acid. That means bromide says, I don't care about a proton. When I'm an HBr, the heck with it. I'll give that proton up. And here, what it's saying to that carbon is, well, look, you want an octet, but I'm happy to have an octet of electrons for myself. Bye-bye, I'm leaving. I'm taking my pair of electrons with me. If something is a very weak base, it's a good leaving group. And the hallmark of a good base is that the conjugate acid has a very low pKa, like negative values or very slightly positive. Let's say 3 or less. Let's say, because there's that borderline area. Let's say sort of 2 or less is going to be a leaving group. All right, so let me show you a conundrum now. All right, so I take tert-butanol, and I treat our tert-butanol with sulfuric acid. And I get isobutylene. This is sometimes referred to as a dehydration because the other product of the reaction is water. And you look at this reaction and you say, well, heck, it looks like an E1 reaction. We start with a tertiary something or another, a tertiary alcohol, kind of like tert-butyl bromide. We end up with isobutylene. Well, that's the same as our E1 product. But he just spent all this time telling me that you need to have a good leaving group. And what's got to be a leaving group, if I just take away OH, is hydroxide. Hydroxide's a good base. It's not a weak base. It's a reasonably strong base. pK of the conjugate acid, water, 15.7. So what gives? So what gives here is the sulfuric acid. So how does it work? Sulfuric acid protonates the alcohol. Say the OH, which leads to a good leaving group. H2O. All right, let me scratch out the mechanism here. Here's our tert-butanol. OH isn't a good leaving group, but sulfuric acid is a darn good acid. In any sort of protic medium, protons are going to come on, protons are going to go off. Sulfuric acid is a super strong acid. The pKa is somewhere in the negative range. So I'm only going to draw out part of my sets of lone pairs here, as is often the case in organic chemistry. We have big molecules. We'll just focus on the part that's undergoing reaction. Electrons flow from the alcohol to the proton of sulfuric acid. Electrons flow back on to the oxygen. This gives rise to protonated tert-butanol. And bisulfate anion. like bromide is happy to take a pair of electrons with it and say, bye-bye, you're stuck with 6. Here's our carbocation intermediate. And now we're in the exact same position that we were in with our previous E1 reaction. Again, I'll draw some protons on one of our methyl groups. So a base that's present can pull off this proton. I'm going to draw it as bisulfate. You can draw it as water too. Basically, you have both bases. In some way, water is probably a little bit more correct. The water is probably actually tied up with additional sulfuric acid because I'm basically indicating you're just dumping Tert-butanol into con-sulfuric acid. So I think actually I'm a little happier writing it this way. So a lone pair of electrons plucks off the proton. We push in electrons in to give our isobutylene. One thing that this little sketch of a mechanism shows very nicely is that the reaction is catalytic in sulfuric acid. In other words, the sulfuric acid starts at the beginning of the reaction, and although it undergoes reaction, by the end we've regenerated it. So one molecule of sulfuric acid can decompose many molecules and dehydrate many molecules of Tert-butanol to isobutylene. Now, I haven't really talked about stereochemistry here. Any example I could give you would be a little bit contrived because it would be very hard to get a tertiary halide enantiomerically pure. But imagine for a moment that we did have a stereocenter, whether it's a tertiary alcohol with a stereocenter or whether it's a tertiary halide. In the SN1 pathway, where we're displacing, once you form the carbocation, you've lost all stereochemistry. So any products that form from that stereocenter, in the case of the alkene, we have no new stereocenter, but any products that form that are chiral by, say, an SN1 reaction are going to be racemic, or at least at that center we will have a 50-50 mixture of enantiomers. All right, let's take a moment now, since we've been going over in the past, I don't know, I guess 6 lectures, we've been going over all these different reaction manifolds. Let's take a little time to summarize how various alkyl halides react. So, how will an alkyl halide react? And what I'm going to do is just to give us some examples and summaries of various conditions that we can consider. I've already talked about things like vinyl halides, phenyl halides, and hopefully by this point people know that something like bromobenzene is off the table in terms of undergoing any sort of reaction. But we've talked about alkyl halides, and we've talked about tertiary halides, we've talked about primary halides, we've talked about secondary halides. Secondary halides are the ones that are the funniest because they have the most pathways available. We've talked about reactions in the presence of strong bases like alkoxide anion. We've talked about reactions in the presence of things that are good nucleophiles but aren't such strong bases. So let's try to summarize, and I'll start with tertiary halides. So tertiary alkyl halides with strong bases, like alkoxide, we see E2 elimination. With weak bases and nucleophiles, we can see E1 and SN1. So let me take a couple of examples. Tert-butyl bromide, or let's just make it tert-butyl chloride just to give us a little bit of variety here. Tert-butyl chloride with, let's say, hydroxide, something say from sodium hydroxide or potassium hydroxide, sodium or potassium as a counter ion. Strong base, tertiary alkyl halide, classic conditions for an E2 elimination reaction. We're going to pull off those beta protons with that strong base and give rise to, in this case, isobutylene. A weak base, let's say water, solvolysis conditions. Water is a weak base, so basically this is the reaction that I just started today's class with. We're going to see some SN1 displacement and some elimination. We wouldn't necessarily be able to predict how much of each we'd see, but it's reasonable to expect some of both products. We saw in the case of one specific condition, set of conditions, heating an ethanol at 55 degrees with tert-butyl bromide, we saw that it was slightly in favor of the SN1 pathway. All right, let us now consider primary halides. Tertiary and primary are the ones that are a lot easier to get a handle on, and so we'll consider primary next. So for primary alkyl halides, we've seen lots of examples with SN2. We've seen some examples with E2. I'll say for sometimes E2. In other words, it wouldn't be the first thing I'd think of, but there are definitely some conditions where E2 elimination can occur. But what we're almost never going to see is an SN1 or an E1 reaction. Why? Because SN1 and E1 pathways require the formation of a carbocation. And primary carbocations are really unstable. You don't get hyperconjugation. You don't get lots of beta. Well, you do from one carbon, but not from others because you only have one carbon attached. You don't have lots of CH bonds on a beta carbon donating in electrons to help that carbocation feel less like it has an incomplete octet. So let's take a look at some categories and try to further make sense of our primary alkyl halides. Good nucleophiles. Lead to SN2. Most bases lead to mostly SN2. But if we have very strong bases, and particularly bulky bases, we get more E2. So I'll say, but bulky bases. E2. I'll say more E2. Let me give you, this sounds really abstract. This is why I hate writing stuff out as words and why trying to summarize organic chemistry in words rather than thinking through mechanisms doesn't work. I mean, these words mean almost nothing on their own. Let's take a look at examples and see, help add some meaning to the words. Different examples is bromoethane, CH3, CH2Br. What's nice is all of these really are archetypes. All of these examples that we're seeing are generalizable. Within parameters, oh, there's some beta branching that's going to lead to more E2. This is sterically hindered. It's going to be less good at SN2. But let's use ethylbromide. All right. Sodium thiomethoxide. Sulfur anions are good nucleophiles. The sulfur is very big. The electron cloud is spread out. The thiomethyl group is basic, but it's not too basic. The pKa of a thiol of CH3SH is about 11. So CH2, a CH3S minus is basic, but it's not really strongly basic like, say, hydroxide. And the sulfur, the clouds of electrons are spread out. It's polarizable. It's a good nucleophile. Lots of things are good nucleophiles. Iodide is a good nucleophile. Azide is a good nucleophile. Halides are reasonably good nucleophiles. This is classic SN1 conditions. Basically, sulfur is happy to share its pair of electrons. It's not hanging on to them too tightly. It's not a strong enough base or bulky to do an E2 elimination. So we get an SN2 product. Let's take our same bromoethane and let's treat it with hydroxide. And again, I could write the counter ion. If I needed a reagent, if I went to the stock room and said, give me some hydroxide, they'd look at me funny. They'd say, well, what hydroxide do you want? Okay, how about some sodium hydroxide or potassium hydroxide? Right, like sodium plus. Okay, hydroxide's basic. But as I said, primary alkyl halides in general tend to undergo mostly SN2 reaction. And in fact, this example, where we have essentially no steric hindrance here. We have no beta branching, no substituents here. It's not like our isobutyl bromide that I showed you in the previous, a few days ago. We're going to get exclusively SN2 displacement to give ethanol. All right, Third example, and by the way, these examples are taken from real experiment, so I'm not just pulling these out of my head. Somebody actually tried this. I mean, that's how people figure out how chemistry works. You do experiments, you analyze products, and then you look for patterns and say, what are the rules here? And then you look for underlying theories. Why does this work? So it didn't start with an understanding of hyperconjugation or steric hindrance. It's like, oh wait, we see patterns here. What do these patterns mean? All right, so last example, bromoethane and a strong bulky base, potassium tert-butoxide. I'll draw the solvent on this. There's no reason I couldn't have drawn the solvent for this. I could have said sodium hydroxide in water, sodium thiomethoxide in ethanol. But I'll draw tert-butanol, potassium tert-butoxide in tert-butanol. Johnny or Buck would take a piece of potassium metal, throw it into tert-butanol, stir it around, it would fizz slowly until all of the potassium had dissolved to give you potassium tert-butoxide and hydrogen gas. And experimentally, here we see exclusively, or almost all, ethylene, I'll say, is the major product. So in other words, first example, SN2, good nucleophile. Second example, although hydroxide is a base, many bases undergo SN2 with many alkyl halides. Primary alkyl halides do undergo SN2 with bases. But if we really push it and we make that base very crowded, so it's hard to get in to form that trigonal bipyramidal, this transition state, with 5 things crowded around a carbon for a fleeting moment, for a fraction of a femtosecond, then we pull off the beta proton mainly and get mainly the E2 elimination. All right, I've put off the most potentially confusing for last, or secondary halides. And those are the ones that really can give many interesting pathways, and also the ones that typically one encounters stereochemistry with, just to make things really interesting. All right, so what can I say for secondary alkyl halides? Maybe the best way to summarize it, SN2, SN1, E2, E1 is, it depends. All right, let's try to make some sense of some complexity here. Strong bases give rise to lots of E2 elimination and possibly some SN2. Bases like alkoxides, hydroxide, amide, anion, NH2 minus, I'll say E2, and possibly some SN2. Those are so much words. Words don't mean very much without example. So let's go ahead and try 2 different examples. I'll take bromocyclohexane as an example here. And let's, as a base, treat it with sodium methoxide and methanol. Why sodium methoxide and why in methanol? Well, if Buck or Johnny took potassium and threw it into methanol, they'd get potassium methoxide, but it might blow up on them or catch fire. If they take sodium, it's less reactive, it's less electropositive than potassium. It's not going to blow up on them or catch fire. if they were, and methanol, the reason I'm saying often we pair sodium with methanol is because methanol is less sterically hindered. If in the other example we put sodium into tert-butanol, the reaction is really slow. Okay, anyway, so you got your sodium methoxide and methanol. Maybe you even bought it as a solution. You throw in some cyclohexyl bromide. It's a secondary bromide. You've got a strong base. The major product that you're going to see is the elimination. I'll say major, and this is an E2 elimination, so I'll write E2 parenthetically. And you might see a little bit, depends on your secondary alkyl halide, depends on the steric hindrance of the base. Maybe in this case, I don't know the numbers from experiment, but maybe about 10% of the ether, I'll say minor SN2 product. Sodium methoxide is not very sterically hindered. It's just that little methyl group. If we go and we move from sodium methoxide to, say, potassium tert-butoxide, I'll say KOTBU, potassium tert-butoxide, and tert-butanol. We can also dissolve potassium tert-butoxide in dimethyl sulfoxide, another polar solvent that's used. Bulky base, secondary halide, all we're going to see is E2 product. I'll say only product. All right, let us conclude by talking about some good nucleophiles. So again, secondary alkyl halides, but let's say with good nucleophiles, like thiomethoxide or azide or iodide, anion, we're going to see mostly SN2. So if I take our bromocyclohexane, take sodium methoxide, sodium thiomethoxide, we'll get SN2 displacement, thioether formation. Last category that one typically encounters is conditions where you have weak bases with polar solvents and sometimes maybe some heat to speed things up. Weak bases don't favor E2 elimination. Heat favors the formation of carbocations. Polar solvents favor the formation of carbocations. So if we have something like tert-butyl bromide and we treat it with, say, water and we heat this, these are the types of conditions that give rise to carbocations. These conditions give rise to SN1 and E1 type products. In other words, these are conditions that lead us to ionize, to form cyclohexyl carbocation, and for it to then partition between SN1 displacement and elimination. All right, well that summarizes what I would like to say about SN2, SN1, and that brings us to the end, E2 and E1. That brings us to the end of our course and to the final.